In this first demo of the series, we will show basic concepts of the Spark language and introduce the Examiner tool from the Spark toolbox. Let's start with a project consisting only of package specifications. For example, this could be the result of low-level design or the basis of an agreement with a subcontractor. We have three packages in this project. A package money defines the amounts and arithmetic operations over amounts. A package identity defines the name and unique identifier that make an identity. The main package database defines accounts and a simple API to manipulate accounts, add and delete them, deposit or withdraw money. A first observation is that all Spark code is valid Ada code, which can be compiled with the GNAT compiler. Let's check this is a valid Ada specification. In order for this specification to be valid Spark, we must check two things. First, that the code respects the Spark restrictions, and secondly, that the annotations are valid Spark annotations. The GNAT compiler can help with the first point. Suppose we make account num a derived type, which is not allowed in Spark. This error is detected by the compiler. The complete check that both code and annotations are valid Spark is done by a tool called the Examiner. Let's check this is a valid Spark specification. This file contains 4 different Spark annotations that I will present briefly. The first 3 annotations are attached to packages. First, the inherit annotation serves a dual role to the Ada with clause. A with clause in Ada gives complete visibility over the withed package, included embedded packages inside the current package. A Spark inherit annotation limits this visibility to what the user declares for a better control over data and control dependencies. Then, an own annotation introduces a logical piece of state, something that subprograms in the API of database will read or write. Here, the state of the database is made up of 2 parts. One part to manage identity data and one part to manage balance data. This annotation is key to manage data and control dependencies in Spark. The initializes annotation states which parts of the state are initialized at program startup. This is used to detect reads of uninitialized global variables. The last global annotation is attached to subprograms. It is used to declare which global variables or parts of the logical state are read and written by each subprogram. So for example, adding and deleting an account modify identity data but not balance data. On the contrary, a deposit or withdrawal modifies balance data but not identity data. All the data and control dependencies of the database are thus declared before the code is written. Let's now consider the complete project where the database is implemented. The implementation describes types to relate each account to its owner and to store the current balance of an account. The data is simply stored in 2 arrays. The implementation of the subprograms from the API reads and writes into these arrays. A crucial step at this point is how the logical pieces of state declared in the specification relate to actual global variables in the implementation. This is the purpose of the own refinement annotation. This is not necessarily a one-to-one correspondence. as shown by the refinement of logical identity data into the concrete array accounts and integer last account num. Then each subprogram implementation must declare which global variables it reads or writes in a global annotation. The examiner checks both that this declaration corresponds to the implementation and that it refines the promise made in the subprogram specification. Let's change accounts to accounts balance in the annotation of add account. The examiner detects the mismatch. The analysis of the examiner also gives the strong guarantee that there are no reads of uninitialized variables in the program. It does so by interpreting more strictly the in and out modes of subprogram parameters than the compiler. Suppose that the programmer mistyped account for last account num in add account. The examiner detects the error. It is important to understand that the static analysis performed by the examiner is exact, so all errors are reported, and there are no false warnings. To summarize what we saw, the Spark language allows a detailed description of the data and control dependencies in a program. Furthermore, Spark supports an abstract description of dependencies in the specification and a concrete refinement of those dependencies in the implementation. A Spark tool called the Examiner enforces these dependencies and gives the additional guarantee that the program never reads uninitialized data.